From the mind to the eye, designing and 3D printing novel glaucoma drainage devices. Dr. John Davis Akkara, Dr. Narayanan Balakrishnan, and Dr. Anju Kuriakul. The authors have no financial interest in this presentation.
I am Dr. Narayanan Balakrishnan, and I am a practicing glaucoma consultant at Sri Ramchandra Institute of Higher Education and Research. My colleague, Dr. John Davis, and I are practicing glaucoma consultants, and in this video, we have attempted to make an innovative glaucoma drainage device that can be implanted in animal eyes, which can help young ophthalmologists to practice implantation of this device and help in future implantation of glaucoma drainage devices in everyday practice. Glaucoma drainage device is the mainstay of treatment of uveitic glaucoma, glaucoma post-penetrating keratoplasty, in neovascular glaucoma, and in patients who've had failed trabeculectomies. But the implantation of these glaucoma drainage devices are very difficult and require a long learning curve. The implantation of these devices are also very expensive, and hence it deters young ophthalmologists from buying them, practicing them, and then using it in human eyes. So through this innovation, we have attempted to make an interesting glaucoma drainage device which has been 3D printed and hence has been used in animal eyes.
Hi, I am Dr. John Davis Akkara, glaucoma consultant at Sri Ramchandra Institute of Higher Education and Research. I used 3D computer aided design and 3D printing to design and print the glaucoma valves that we are talking about. So I used a free software called FreeCAD and drew the design of the valve which I had in mind, and that was the footplate. And once I had drawn the design and finalized it, I took it to our 3D printing lab at campus and used the resin 3D printer to print the model. There are two types of easily available 3D printers. One is the resin 3D printer, and the other is the plastic 3D printer, which uses spools of plastic. Once the 3D printed footplate was printed, I removed it from the mold, cleaned it with isopropyl alcohol, and then kept it under UV light for it to harden. And once that was done, the footplate was ready to use. I used the tube from a Venflon, an 18 gauge Venflon, to make the tube of the valve. Once the tube was cut, it was inserted into the hole of the footplate. And so this is the footplate and the valve mechanism, and that is the tube that is inserted into the anterior chamber or pars plana. So if you look at the other side of the valve, you can see the fine canals. There are 6 canals opening in 3 in each side. These allow the liquid to flow in from the tube. We also injected fluorescein dye through the tube to see the flow of aqueous into the valve. See the air bubble which block the canals first. So even a single air bubble can prevent proper drainage through a valve. Thus, it is important to prime the valve with saline during the surgery. We then fixed a bow tie in a plastic container and did a conjunctival peritomy to insert the valve. The footplate of the valve is carefully inserted under the conjunctiva. Make sure that the conjunctival opening is big enough to accommodate the footplate. The footplate has a larger surface area than the cornea. The tube is left pointing upwards towards the cornea. The footplate is then anchored to the sclera by suturing through the 4 holes using vicryl sutures. The tube is then measured and trimmed with the scissors. The scissors are kept at an angle so that the tube is cut in a bevel shape. Once this is done, the next step would be to implant the tube into the anterior chamber. But for that, first we have to make a track using a needle, partial thickness through the sclera into the anterior chamber in case of a phakic eye, and into pars plana in case of a pseudophakic or aphakic eye. So now that partial thickness cut tunnel has been completed, then next step is to insert the tube into the tunnel so that it reaches the anterior chamber. Once the tube is inside, we have to make sure that it does not touch the endothelium. That's all for the surgical part of the video. These are some of the other valves that we 3D printed compared to the first valve, which was actually quite big. Let us now look at some of these newer valves in detail. We basically designed three different models of valves of three different shapes and sizes. This is what they look like. The biggest one is the first GDD that we implanted in the surgical video. There is the small one with the tube, which is the latest design as of now, and there is also a medium sized one. For testing the flow of all these valves, we extracted fluorescein sodium from the strips using alcohol and took it in a 1 ml syringe. This is a top and bottom view of the first valve that we designed. We can see the flow of fluorescein dye through all the 6 channels in the valve conduit. This is observed under cobalt blue illumination under a surgical microscope. Here we can see the 6 conduits for the fluid to pass through the valve, and if you lift it up, you can see the external hole into which the tube is inserted. The 4 holes on the plate itself are for fixing. On higher magnification, you can see the 3D print lines of the valve. This is a medium sized valve, top and bottom view. On higher magnification, we can see that it is quite flat. It was easy to insert, but the valve inside was too narrow and not allowing the liquid to pass freely. It was leaking and not entering properly. This is a design for the smallest and newest model that we had designed. This has a raised area on the top through which the tube is inserted, and it has multiple channels which channel the liquid into the bottom. The plate itself has multiple holes to allow easy fluid pass through into the subconjunctival space. The fluid flow is as seen in this video. Hope this innovation with 3D printing inspires young surgeons to start doing glaucoma valve surgeries and also to design newer models of glaucoma drainage devices. Thank you.